Lesson 12.2b on dependent events. Let's start with a little bit of a review. Say you're drawing a card randomly from a deck of playing cards. What are the odds you draw a spade? Well, to calculate these odds, let's first look at how many total cards we have. 52. Of those 52 cards, 13 of them are spades. So the probability that we draw a spade from a deck of playing cards would be 13 out of 52, which reduces to 1/4 or 25%. Say we change a problem slightly. Now let's say that we draw a card twice. Each time we replace the card and reshuffle the deck before the next draw. Now what are the odds that you draw 2 spades in a row? What hasn't changed is that the odds of drawing a spade each time are 1/4. But now we have a sequence of 2 independent events for which we have to calculate the probability of each event. Well, if we actually have 2 events and they're occurring one after each other, the odds of drawing a spade in each event are 1/4. So to calculate the odds for a set of multiple independent events, we just find the product of the individual odds for each event. So 1/4 times 1/4 equals 1/16, or 6.25%. Let's change the problem now. Now let's say that you draw 2 cards in a row without replacement. In other words, after drawing the first card, you don't put it back into the deck before drawing the second card. Now what are the odds that you draw 2 spades in a row? What's changed in this problem? I'll give you a hint. It's in italics. Without replacement. In this probability experiment, we're actually drawing 2 cards in a row without replacing one card before drawing the next. Much more akin to what would happen in a game of blackjack or a game of poker or any other type of game of cards. But that actually changes then the type of probability that we need to calculate. Here's why. Let's say that we try and study this type of probability game here. Well, it's still a sequence of 2 cards being drawn, so let's look at it as a sequence of 2 events. In the first event, we have 52 total cards. 13 of them are spades, so the odds of actually drawing a spade from a deck of cards is still 1 out of 4, 13 out of 52. I'm going to keep it as 13 out of 52 instead of reducing the fraction just for the sake of intuition here. But in the second event, since we have 1 less card from the deck and we have 1 less spade in the deck, that's now changed the probability. Now there's only 51 total cards remaining in the deck, and only 12 of them are spades. Which means that the odds now that we draw a spade in the second draw are only 12 out of 51. But since this is still a sequence of 2 events, we take the product of these odds of each individual event to calculate the odds or the probability of the entire combined event happening. So in this particular case, we take 13/52 times 12/51, and then when we simplify that fraction, it works out to be 1/17, or approximately 5.88%. Slightly different odds than the previous outcome, where we were actually drawing the card each time with replacement. So now that we've actually changed the game to drawing the cards without replacement, it actually affects the probability. Why? The change here is actually the difference between the previous lesson where we were studying independent events and this lesson where we're studying dependent events. Now, what are dependent events? Dependent events are when the outcome of one event influences the outcome of another. For example, in order to calculate dependent events, we have to change the actual probability slightly. And that probability, we also have to change the notation. Here's what the notation looks like. The notation, the probability that event n sub 1 and event n sub 2 happen together is equal to the product of the probability of n sub 1 times the probability of n sub 2 given n sub 1. In other words, the odds of that second event occurring depend on or are influenced by the outcome of the first event. So when we actually notate the probability of n sub 2 given n sub 1, we use a vertical line between those two events in our notation there. Here's another example of a probability experiment that actually involves dependent events. 2 students are randomly chosen from 5 students, 3 of them female, 2 of them male. What are the odds that both students randomly chosen are actually female? Well, if we structure this again in terms of 2 events, here's the first event. We know that there's 5 total students to choose from, and we know that 3 of them are female. So what are the odds that a female is randomly selected in the first event? Well, 3 out of 5. But now, in the second event, we have 1 less student to choose from and 1 less female to choose from. So in the second event, what are the odds that, again, a female is randomly chosen? Well, with only 4 students remaining and 2 of them being female, the odds are 2 out of 4. Multiply these 2 probabilities together to calculate the odds of the entire experiment. 3/5 times 2/4 works out to be 6/20, which reduces to 3/10, or 30%. Let's do one final game here, one final experiment. Lottery. Everyone loves gambling, right? So, in the Powerball lottery, there are 59 white balls and 39 red balls. One Powerball drawing consists of selecting 5 white balls from the 59 that are there, and then 1 red ball, otherwise called the Powerball, from the 39 red balls available. What are the odds that your ticket wins the Powerball drawing? So when you actually buy a ticket, you are randomly given 5 Powerball numbers and 5 white regular numbers and then 1 Powerball number, 6 numbers in total. What are the odds of actually winning this game? Well, we have 6 events here. We have, in structuring the problem, we have 6 events. First, we have 5 drawings for 5 white balls. And then we have 1 drawing for the red Powerball. So, 6 total events. Now, what are the odds for the first 5 drawings, the first 5 events? When drawing each of those 5 balls, well, we have 59 total white balls to choose from. And we have 5 numbers that we've selected in our lottery drawing. So we want 5 out of those 59 total numbers available. So in the first event, we could draw 5 possible numbers that we want out of 59 numbers to select from total. But in the second event, there's 1 less number, there's 1 less ball to select from, and 1 less number on our ticket that we want to have drawn. So the odds in the second event are only 4 out of 58. Then in the third event, there's only 3 numbers remaining that we want out of 57 numbers remaining, and then 2 out of 56, and 1 out of 55. Then in the red Powerball drawing, there's 39 total balls to select from, and there's only 1 number on our ticket that we want. So the odds of drawing the Powerball, or at least drawing the Powerball that we want to have drawn, is 1 out of 39. So to calculate the total odds of selecting 5 white balls and then 1 red ball from the 59 white balls and 39 red balls to select from, the total odds, we multiply each of these individual odds together from each individual event. And the total odds of you winning the Powerball with 1 lucky ticket is 1 out of 195,249,054, which works out to be approximately 0.000000512%. Here are the classwork problems to do for today.